Okay. Okay. So I think we can start. So hello everybody. This is Luboš Pirkl and Radek Máca from CFD support. Hello Radek.
Yeah, hi Luboš, hello everybody.
So we would like to welcome everybody to the webinar on Turbo Machinery CFD, which is a smart, easy and affordable CFD software for rotating machinery. I hope everything works well, all the technique is fine. And anyway, in case of any technical problems, feel free to contact us and we will gladly answer all your questions and comments. The webinar is being recorded and its recording will be made available on our YouTube channel. And the topic of today's webinar is an axial pump. So we would like to show you how easy it is to simulate an axial pump in Turbo Machinery CFD. I think it's time to get to the action, so I think we can start. So let me start with who we are. So please let me say a little bit about us. So this is me. My name is Luboš Pirkl. I'm co-founder and managing director of CFD support. And today I'm sitting here in our Prague office with my colleague Radek Máca. So hello Radek. Hi.
Hello again.
So are you ready for the webinar?
Yes, I'm absolutely am. So please go ahead.
Okay, I will only note that Radek is our senior developer here at CFD support and he will take care of the technical part of today's webinar. And yeah, so I think we can start. Perhaps we can switch the camera off and let's go. So the webinar is going to take about 1 hour, depending on the number of your questions and comments. There will be 3 parts in this webinar. In the first part, I will give a general introduction to Turbo Machinery CFD. I'm going to point out the main Turbo Machinery CFD features and benefits. In the second part, there will be a live example where Radek is going to show you how to simulate the axial pump in Turbo Machinery CFD. And finally, in the last part, there will be a Q&A session dedicated to your questions and our answers. Feel free to put your questions. There's a special window below where you can put your questions, and we will answer them later in the webinar. Especially in the beginning of this webinar, we are going to be quite general, but feel free to put your detailed questions, and we will gladly answer them. Okay. So I will start with CFD support. So I will say just a little bit about CFD support. So CFD support is a private engineering company dealing with mainly computational fluid dynamics. We are located in Prague, Czech Republic. And for our clients, we are used to deliver complete CFD engineering projects. We do projects on demand all across the CFD field. We also do quite a lot of outsourcing work. Then we deliver extensive OpenFOAM training and consultancy, as well as OpenFOAM support and custom development. But of course, our flagship product is Turbo Machinery CFD. So, which is today's webinar about. That brings me to Turbo Machinery CFD. So I will just give a brief description of what Turbo Machinery CFD is. So Turbo Machinery CFD is a unique software based on OpenFOAM. It was designed for CFD simulations of all rotating machinery, such as pumps, fans, compressors, turbines, hydro turbines, all of them. Both radial and axial machines, both compressible and incompressible fluid flows. Turbo Machinery CFD is a complete workflow that covers all the engineering steps, from the pre-processing over the simulation to the very detailed post-processing of the simulated results. And what's also important is Turbo Machinery CFD is independent on any other software, and on the other hand, it's fully compatible with standard OpenFOAM. Let me put just a quick review of Turbo Machinery CFD unique value. We believe turbomachinery CFD is unique at least for 4 reasons. Number one is turbomachinery CFD has no licensing policy, which means our clients can keep turbomachinery CFD forever, and they can use it for unlimited number of users, jobs, or cores. This gives the investment in turbomachinery CFD a permanent value, and also this means our clients can scale their CFD simulations in a really big way. Number two would be turbomachinery CFD is fully automated, which means all the workflow from the initial data to the final engineering results can be run by a single click or a single command. And for this reason, turbomachinery CFD is extremely effective. Number three would be we deliver extraordinary technical support. We keep custom approach to every customer, to every issue. We never leave behind any of our clients. We are very flexible in it. We support our clients even in matters out of the turbomachinery field, for example, in numerical mathematics, physics, CFD, IT, or even software engineering. And finally, the real tutorials are included in turbomachinery CFD, so the users have no doubts about the best practice settings. The real machines are included and already preset, and that makes turbomachinery CFD ready to use and easy to use. Okay, there are many other benefits for turbomachinery CFD. I'm not going to go for all of them. I will just mention a few of important technical details. So turbomachinery CFD is available both for Linux and Windows operation system. The workflow is very the same, both in Windows and Linux. The graphical interface is available. We have developed completely from scratch, or we have delivered special set of plugins for ParaView, which makes ParaView the preprocessor and also a processor and post-processor for turbomachinery CFD simulations. The turbomachinery CFD is transparent project, so the trial version, the demo version, is available for everybody for 1 month, so anybody can try turbomachinery CFD and decide to go for it afterwards. The real tutorials are included, so it's very straightforward working with turbomachinery CFD. HTML reporting is available, so anytime during the simulation or after that, the users can see the results immediately and take the action. So it's very easy to use for this. We have developed also a special set of post-processing plugins in ParaView called TurboBlade Post. Turbomachinery CFD is scriptable, so it can be scripted and connected with. It can become easily part of another workflow or workflows and part of bigger picture, not just a simulation of a rotating machinery. It's easily customizable. The GPL parts are delivered together with source code, so it's very easily customizable, and it's the development is the user driven. So we are very carefully hearing our customers and do our best to make it as usable and as good as our clients want to have it. And many resources are available online on our website, so you can take a look. Okay, which brings me to the live example. So it's now I will switch the presentation to Radek, and Radek is going to show you the real example how to simulate the axial pump with the external mesh. So Radek, are you ready for your part of the presentation?
Yes, I am.
Okay.
I'm ready.
Okay, thank you. So I'm switching presentation to you.
All right. So now you should see my screen, right? Perfect. Okay. So hello again. So today I will show you an example of usage of our turbomachinery CFD. So today's case will be the axial pump. So I will show you which data I'm using for today's webinar. So afterwards you can, for example, try it by your own if you ask us for the trial version. So here in the download section, in download cases, here you can find the Axial pump tutorial or test case for our TCFD software. So basically here you can easily download it by filling this form, and then you can download this case, which I have done before the webinar. So I will jump into my directory in which I have this case extract and stored. So basically this is it. And at the beginning, basically you need just the input files for defining of the computational mesh. Basically you have two options. First one is just to input the surface geometry, which defines your machine and or your case, or as in this case you can input the external mesh from wide range of commercial or open source measures. So today I'd like to show you, for example, today we will use the mesh from the Fluent. So basically I will just simply by a few clicks I will show you how to convert the mesh from for example from the Fluent software to OpenFOAM. So here I have the Axial pump in the MSH format, and now I'd like to convert it for OpenFOAM purposes and for our software. So I will just run standard OpenFOAM for Windows, our version 17.06. I will find my my mesh on my disk. So I will just run my favorite file browser, Midnight Commander. Okay, I will enlarge it a little bit. So here, mesh convert, here's my original file. And here I have created the case in which I would like to convert this MSH format to OpenFOAM format. For this, I just need the simple OpenFOAM structure. So now there is a simple command for converting Fluent mesh to foam, because this is the 3D mesh. So I will just run this Fluent 3D mesh to foam application, and the input is the name of the external mesh. So I will run it. It tells a lot of information, but at the end I can see the mesh directly in OpenFOAM format. So by typing parafoam, clicking on apply, I can nicely see the input mesh visually. So this is the mesh for our case. Before I will load it into our software, I need to just split into four parts. Maybe I was too fast, because this geometry consists of four separate, let's say, separate parts. So first one is the, let's say, inlet pipe, then we have the impeller, then we have the stator part, and outflow pipe. So on this case I will show you how to set the mesh, this kind of mesh where we have four regions, and moreover we have the periodic segments. All parts are not constructed or are not generated as a full wheel, but only as some segments. So this will be loaded to our TCFD software. So to split the mesh, there is a simple command which is called split mesh region. I will just tell him that I would like to split the mesh using the cell zones, and this is it. So I will run this utility. It basically splits the mesh into four separate regions, which can be loaded into our software. So now in constant, so in 0 file, we have this four meshes which can be loaded into our software. So basically, I have created the mesh here. So basically, this is what you can download directly from our web pages without this converting approach and converting work. Okay, so this is our input. So I can directly run the TCFD software. So now we are using 17.06, but within 1 month, we are going to release the brand new version 17.10, which will have a lot of new features. So I think we will introduce these new features in upcoming webinar. Okay, so this is the graphical user interface. It was directly implemented within the ParaView software, which is really nice and comprehensive tool for scientific theta And here, the so-called TCFD source. This is these tables using which you can set up a whole case and you can run the simulation. So you can start really from scratch by setting every part of these menus, but just to make this, because we have only limited time, so I have preset some configuration file, because all you can fill here you can save in the configuration file, and then anytime you can load it again. So I will go to my working directory, which is here. Today's webinar we have here. Yeah, and here I have configuration file which is called Axial pump no mesh, because I'd like to show you the principle of defining the mesh from very beginning. So I will load this configuration file. So this configuration file contains all necessary setup for the simulation except the mesh definition. So basically, here is defined the coordinates of the pump, the geometry properties, the physics. We are using water. The case is incompressible, of course. Our software also provides the cavitation risk. So at the end of the simulation, I will see some information about the possible cavitation inside. Of course, I can choose the turbulence models. I can define several points to be simulated. So basically, I can define several speed lines, so simulation with different rotational speed, and for each rotation I can define several points with different boundary condition. It means with different pressure drops or with different flow rates and so on. In this inlet and outlet menu, here I basically define the different volumetric flow rate. So I will simulate this pump within the different volumetric flow rate to see the efficiency map and to find the best efficiency for point, for example. And I also set the outlet condition as a fixed pressure. So this is this. Inside the simulation menu, you can set basically the time management. So for today webinar, we will use the steady state simulation. If you have a full wheel, you can also use the transient simulation, and in upcoming release, you can also use the transient simulation for periodic segments too. So this is the biggest feature for the upcoming version. Here we can set the processors which will be used for simulation, because my laptop has just 4 cores, so I will decrease this number to 4. There is no limitation, so if you have a big hardware and big machine for computation, you can use any number of processors. The scalability of the software is really nice. We performed some studies about the scalability, so we can also provide the studies to you if you want. So, and of course, numerical order you can change. some advanced menus, which is, let's say, not important at the moment, initial condition, and let's say the most important part is the mesh definition. So at this moment we have no mesh defined, so we will start to do that. So our whole mesh will be or consist of four components. So we say components, one part of the geometry, let's say inlet part, stator part, rotor part, outlet part, and in this manner the mesh is split it. So we will have four parts, for regions, or for components. Here we have a nice figure in which we can see the progress of a definition. So basically now we know we will have the four components, and during the setting of mesh we will see how the mesh is connected to each other, and this is really nice tool for checking the procedure of the mesh definition. So I will start with the component one. So geometry source, first option is to define the mesh with the STL files, but this is not the case. We have an external OpenFlow mesh, so I will choose this option, and now I should find this mesh. So I have to go back into my working directory here in mesh, and here are the four regions. So I will start with respect to the flows through my machine. So I will start with the inflow pipe. So immediately I can click on apply, and the part of the geometry should appear here in my render window. Okay, perfect. So this is my inlet pipe, just the segment. So I can see clearly which component I am defining now. Okay, component name, I can set it to inflow to be more human readable. You can see that this window is really interactive, and immediately you change something, you can see what is happening. Number of periodic segments, because we have not full pipe, we have just the periodic segments. We have to define how many segments builds the full pipe. So in this case, the number is 8. And now here are the patches which is included in this external mesh. So it is transferred from this Fluent mesh, and we can see automatically here. And now we should just assign the correct type of boundary condition. So inflow inlet, which is just the physical inlet into the domain. So the type is inlet, it is easy. The inflow outlet is not a physical outlet, because this component is a neighbor of the next component, which will be rotor. So this is not the outlet, because outlet is used just for the physical outlet from the domain. And in this case, we have these two types, inlet interface and outlet interface. So in this case, this is the outlet interface. Here you can see that there is no question mark, this real number. So using this number, you define the communication between these two components. So I will let it to 0, and then I will explain it a little bit later. So inflow wall, this is just a wall, so there is type boundary wall. This is common usage. Inflow periodicities, these are these periodic boundaries, so it must be set as a rotational AMI, because this arbitrary mesh interface is used for the communication with between these two patches. So rotation AMI, and the same for the other side of the periodicity. And I have to define which, because of course we have more this rotational MA within one component. So I have to make a couple which to communicate between this couple. So I will just click on, I will just use the right mouse button, and I have to define the neighbor of or the partner or the couple of these two periodicities. So if I define it correctly, this cells changes, or this cell changes the value, and it tells me that I have defined it correctly. Inflow wall is type of the wall. Okay, so I can check the apply button and my first component is set. Okay, so what I didn't use is I have to define for every outlet or inlet interface, I have to define the neighbor. So for this component, the neighbor will be the second component. So I will click, I will use the right click and then choose the second component, and I see that this outflow from this inflow component, let's say, is connected to the second component. So I will use the component 2 now. So the same, I will choose external open flow mesh. I will farm the impeller part, because impeller is the second component. I will click on apply. Here I will choose the VTK composite index and sorry, this one. And now I can see that the colors in the render view corresponds to my graph. Again, I can define the name of the component, number of periodic segments. This has also 8 components. And before I start to setting this component, you can see that there is really the interface between the component 2, between the rotor and inflow pipe is really the same. Yeah, the surfaces are same. So I can impose so-called arbitrary mesh interface to this interface for the communication between these two patches. So basically, the impeller inlet will be the inlet interface in this case, and the value 0 means that this arbitrary mesh interface communication will be imposed on this interface. And now I directly can connect it to the first component. And now I can see the solid arrow which shows me that the connection between these two components are set correctly. Okay, so impeller blade is the type simply blade. Impeller clearance is the part in this clearance, because this is the unshrouded case. So I will just set this surface with edges to see the topology of the mesh. So if you can see, sometimes this approach is used to define the clearance mesh. We can see that there is no point-to-point correspondence. I hope you see clearly. Yeah, there is no point-to-point correspondence. So there are arbitrary surfaces on which we should define again the communication between them. So these are arbitrary surfaces to make the procedure of mesh definition easier. So it's also quite common approach. So I have to define, this is the special internal AMI type of the condition to connect these two arbitrary surfaces. And again, I have to make a couple of them. So by right click, choosing the correct patch name, I can make this couple. Great. Impeller hub, it is also easy to define, because here is the type hub. Impeller outlet is again not a physical outlet, but the outlet interface. I can directly connect it to the third component, and you can see really it is connected to the third component. Impeller inlet, I already said. Impeller periodicity, so again the same as for inflow segment or inflow component. So it is the rotational AMI. I have to make a couple. Great. And impeller shroud, we have here the shroud type, right? Perfect. So I can click apply again and go to define third component. So again, external mesh, it will be quick. Now stator, we can define it as stator. This segment has 9 or the full stator part is built using 9 segments. So I can define it, click on apply, and now you can see really the stator part appears. And the setup is again the same. Stator blade is just a blade. Stator hub is again the hub. Stator inlet is inlet interface, and it should be connected to the component 2. Again, the solid arrow shows me that the connection is finished. Stator outlet is still the outlet interface because there is the last component behind the stator. Periodicities, again the rotational MA. I have to make a couple of them, and stator shroud is just a shroud. Okay, in this case, if you see the surface between rotor and stator part are really not the same. Yet it is obvious because we have different number of segments. So on this patch, we can't set the arbitrary mesh interface because the interfaces are not the same. For this approach, or for this case, the so-called mixing plane approach is applied, and basically we used a positive number to define this approach. Let's say for axial machines, a reasonable number is 10, or for this axial pump. So this is this. So we have to define 10. Okay, and I think all is set, and we can go for the 4th component, which is the outlet tube. So okay, outflow is called, so I can define it as outflow. Periodic segments is 9 for this segment, and I can start to defining or assigning the type of patches. The outflow is now really outlet. It is the last component. Inlet is the inlet interface. So I have to define inlet interface and connect to the 3rd component. Okay, again, I can check it here. Periodicities are rotational AMI. I can make a couple of them. I have to make a couple of them. Outlet wall is just, I can leave it as a wall, and outflow wall is also a wall. Again, I should check if I can apply AMI approach or mixing plane approach. I can see that the interfaces are really same, so I can leave the number 0 here. So now we are at the end. What I missed for the component 2, that we have to define the rotation, of course. So we have to define which component will be rotated, and this is component 2 because it is rotor, and we just click here that this component is rotating, and we have to check which part of the geometry also rotates. So the blade is rotating and the hub is rotating. Yeah, the shroud is not rotating because we have this unshrouded case, and there is a clearance between the shroud and the blade. Okay, perfect. So I think that is all. So you can see that I am able to set the mesh within 10 minutes from very beginning. So it's really easy to use. And I think that is all from the setup. Maybe I can stay for a while here because the meshing options are not relevant here because it is for case for which you define just STL geometry. So then these means are relevant. What is important? The post-processing. Here you can define the post-processing options. First one is so-called efficiency probes. So we can basically set which interfaces will be used to compute the efficiency, the pressure drops, and so on. For example, in this case, a reasonable or sensible options can be, so I will add the inlet patch from which the efficiency and other variables will be computed, can be the interface or the inlet to the impeller, right? And the outlet could be the outlet from stator, because I don't want to know the pressure drop of the inlet and outlet pipes, for example. And from which patches the torque will be computed. So I will check the impeller blade and also the impeller hub. Okay, so from these patches, the efficiencies and other parameters will be evaluated. Blade-to-blade views. So you can also set the blade-to-blade views, which will be automatically evaluated after the simulation. It is really simple to define. You just tell which part of the mesh you would like to visualize. For example, we would like to have the component 2. Now we have to define. Now we have to define the hub patch, the shroud patch, because it is needed to generate the blade-to-blade view and field to visualize. So you can visualize any field. For example, a nice view is the velocity with the stream tracer LIC, and you can tell which slices between the hub and shroud you would like to visualize. So this means this is the slice directly in the middle between the hub and shroud. Okay, so you will see at the end of my presentation inside the report. Meridional average the same. You can define meridional average. The default option is inside the rotating components, and the fields which will be evaluated is static pressure. We can, for example, choose the total pressure. And additional data, if you have, for example, for comparison of several computation, you can include the data files to add to compare with the current geometry and current setup. Okay, so maybe we are at the end. So this is my graph of the components, and I see that I forgot something, because as you can see, the arrow is pointing only in the one way and is not solid. So I have to go back to my component setup, and I see that the stator is not connected to the outflow part. So I will go to the stator, and the outlet interface is not connected. So I have to connect this part to the component 4. Okay, and now I am at the end. Or this is how the graph of the topology graph should look like. Every solid line. Okay. All right, so if I'm satisfied with the setup, I can now run the simulation directly. So I can close this window by double click on it. And yeah, now I can run the simulation. So to run the simulation, I will just denote this TCFD source, and now this icon is available, which is TCFD manager, basically a manager for the simulation. So to run the simulation, I have to define the directory name. So for example, my computation. So in this directory, at this path, all results will be stored. So to approve this name, I should click on apply. Now I have to click on write case. So every important and every compulsory files for OpenFOAM and for our software is created automatically. And now I can run all the simulation at once. This run all button basically runs the meshing process. In this case, just is assemble the meshes we have defined, and afterwards it runs the calculation. So I will just first, for example, I will click to mesh all. Basically now the software is touching each component, redefining the types of the boundaries and renaming the boundaries with respect to what we have set. And afterwards, all these parts are merged together and ready for the simulation. So this is very fast. And afterwards, the final mesh is, let's say, is finished, and it changes to the green color. I can run the calculation. During the calculation, you can anytime you can skip to next point if you are, for example, if the convergence seems to be achieved, if you see that, or from many reasons you can skip to next point, or you can abort the calculation anytime of the computation. Okay, now I can run the calculation. So during the simulation, you are always informed about, okay, so maybe I have said something, the geometry, okay. So I will go back, because maybe I missed something in my setup. So I will go back to my TCFD file. For these purposes, I have prepared the correct one. And now I think I can go back, and yeah, now I will touch the run all button. Oh yeah, right. It tells me that because I redefined the input, I should write the case again, and afterwards I can run the simulation. Okay, so now I will run it all. So okay, I will leave it here. So during the computation, anytime you can click on light report to generate, to see what is happening. I will show you later on. And at the end, the full report is created automatically, and which is here. So at the end of the computation, here is my computed case. Okay, I will use this browser. At the end of the computation, inside your defined directory, there is a report directory in which the report in the HTML format is automatically generated. So we can open it in any file browser, and anytime you can see the results. You can share it on your with your colleagues, or you can use in many for many reasons. So it basically contains all important information about the case setup, what machine type, what rotation speed is, the mesh details, how many cells, really the detailed information about the mesh, all important parameters about the mesh. Y+, which is important for the turbulence modeling, time of the computation, how many processor was used for the computation, the residuals, convergence, and there are several bunch of variables evaluated automatically. So first one is, for example, head with respect to the inlet condition, or with respect to the defined conditions. So we have defined 5 points to be simulated. So we can see the head with respect to the flow rate. Also, these values are plotted in a nice figure, and also we can see the convergence process of the head. The second one is, for example, efficiency. So, for example, now we can nicely read that the best efficiency point has almost 88%, and it is, for example, it is achieved for the flow rate 14 cubic meter per second. Again, the efficiency, convergence, the torque, the same for the torque, for your defined points, total pressure difference, total pressure per each interface, so you can see the jumps along your machine, velocity magnitude spread interfaces. Yeah, so really you can go through all values and really make a detailed analysis of the computation of the flow inside your machine. And the last but not least is the cavitation risk, which tells you the risk of the cavitation for your machine. For a given point, you can read, for example, the percentage of cavitating volume and cavitating surfaces. So you can nicely, or you can directly see if on your machine will be problem with cavitation, and then study in more details. Also, the cavitation index is included in the computation and evaluation. So you can also read this cavitation index. Because we have defined the blade-to-blade view, so it is generated and rendered automatically. So for example, this is blade-to-blade view at the height 0.1. It means it is the radial coordinates at 10% of overall height, and the 0 means it is a hub, and 1 it means it is a shroud. So this is the slice in the neighborhood of the hub, and nicely you can see the streamlines and the velocity magnitudes along the blades. So you can check what is happening for each point at the hub. So now here we can see the nice streamlines, smooth flow around the blades. In the middle, again, for each point, it also looks quite nice. And near the shroud, we can see some recirculation, and using this, for example, this information, you can propose some modification of the blade, for example, to increase this recirculation. This is the meridional average, so the pressure drop along the rotor blade, nicely visualized. Okay, so this was the full report, and now I can go back to my simulation just to show you what is happening. You can see here is the information about the point which is simulated, how many iterations is already done, and how many iterations are resting, let's say, the overall time of the computation, and so on. Anytime, as I said, you can generate the light report, which is generated really fast, and you can see directly here in ParaView, and for example, check the actual residuals, if what is happening with your computation. So this is light report with a graph of residuals, flow rates, with the head, which is already computed, and with the efficiency. So at the moment we have only a few iterations. So this is this. Okay, so this is really nice. And this was the automatical evaluation. And give me please just 1 minute to show you some evaluation which you can done directly in ParaView or your visualization. So basically, you can anytime you can load the case form using this button, which is here. So here you can click on the show results, and the results is automatically shown and appear in the render view, and you can work with them. So you can play around, you can visualize full geometry, what you want. You can visualize the total pressure distribution along the geometry. You can just visualize the surfaces of the stator and rotor part with the static pressure distribution, with the contours. So you can use any advanced filters directly delivered with ParaView or delivered by our company. So this is the meridional average and turbo unwrap. And last but not least, because we have enabled the cavitation risk, so we can visualize the blades or the cells in which the cavitation risk is positive, let's say. Yeah, so you can nicely analyze the places in which the cavitation occurs. So maybe my time is up. So I have to give the presentation back to Luboš. So Luboš, can I, or could you take my presentation?
Yes, of course, Radek. Thank you very much for your part of this presentation. It was remarkable. I enjoyed it very much. So I'm gonna finish the presentation. I'm gonna finish with my almost last slide, which is called how to get to Turbomachinery CFD. So first of all, the trial version, the demo is available, so anyone can try the full version of Turbomachinery CFD for 1 month, and after that, he or she can decide to take the action or not. So it's very transparent in this. There's nothing to lose. If you like it, you can try. About our business model, so Of course, turbo-machine CFD is a business project. So the business model is different from standard commercial codes. It's very different. So the paid version of turbo-machine CFD is always perpetual, and our clients can keep it forever and use it for unlimited number of users, jobs, or cores. And what is paid for, and this is really important, what is paid for is the first delivery and later technical support, updates, and maintenance. Right? So I will repeat it. I think this is really important. So it's always perpetual. You can use it for any number of users, jobs, or cores. And what is paid for is the first delivery and later technical support, updates, and maintenance, which is agreed at the beginning for a certain period of time. Yes, we believe turbo-machine CFD is very affordable. Last year we decided to fight hard for the universities, so we have special program for universities with outstanding conditions. So yeah, and the most of our clients are of course private organizations. So feel free to contact us. We will gladly tell you all the details about the pricing. Yeah, and which move us to the last part of our presentation, and that's Q&A session. So I would like to kindly ask you to put your questions, and we will gladly answer them. So yeah, just take your time and take your chance and really put your questions, and we will answer them. Yeah. So far I cannot see any question. So let's make it easy. So this is the last call. So just put your questions, or if you have one. If you don't, we will conclude. So let's give some more time. Just okay. Let's give it another minute. Maybe I can switch to Radek. Radek can move with the turbo-machine CFD with the results. Just give it one last minute, and then we will conclude if we will get no question. Okay, maybe I can say, because we usually have lots of questions, so maybe I can say that people usually ask about the design tool. Well, of course, CFD support and turbo-machine CFD is just a simulation tool, right? So the initial geometry has to come from somewhere, either from some CAD system or whatever you have, or of course from some design tool. We have very good experiences with CF Turbo software. CF Turbo is a special software for designing all rotating machinery. It's a product for German company CF Turbo, the same name. They are located in Dresden and Munich. They have developed really unique and user-friendly and great tool for designing of all standard rotating machinery. CF Turbo has its interface especially created for turbo machinery CFD, so we use that tool, and we always export the data to turbo machinery CFD in CF Turbo, and then we simulate, and we can recommend that. I can see the first question we have finally. So from Pradeep, a quick question: does it have a mesh tool included, or you use different meshing tool? Right, I like this question. So I will, because it's very simple, I will answer it, Radek. Okay, so yes, of course. In this particular webinar, we decided to go with the external mesh, right? But of course, turbo-machine CFD has internal meshing system. It's very robust, very effective, automated, and it's based on snappy hex mesh tool. Radek is showing it right now. You can say you open the directory with STL files with the CAD data, so with surface format, of course, STL, stereolithography format, and the workflow is very similar, a little bit different, but very similar. And of course, we recommend it as a first choice, but there are some other clients ask if they can use their own external meshes for historical reasons. They have Mesher, for example, and lots of meshes in MSH or other formats, so of course they can load it. And these two choices: you can load external mesh, or you can use automated meshing system in TurboMachinery CFD. So I guess this is answered by me. Yeah, another question from IGNAD. The technical support is included in the project cost. Yes, of course. Yes, of course. Basically, we can say that's what you paid for, right? You can view it as like the software would be for free, and what you pay is the product's technical support and updates and maintenance. That's basically what you pay for. And of course the first delivery, but it's the in fact it's the technical support what you paid for. The technical support is always agreed for a certain period of time. So for example, typically for 1 year or for 2 or 3 years, then we give you the offer, you take it, and anyway you can keep TurboMachine CFD forever. But after the agreed period of time, you can decide to go with us ahead or not, right? That's really important. So you can anytime decide, I don't want to go with you again, and you can keep everything, you can use everything forever in unlimited way. And that's, by the way, it's a good reason for us to be well motivated to assist you with everything, to make you happy, because after the year you can decide not to go with us, but you can keep everything. So we are very good motivated to help you, to do our best to make you happy. Okay, the next question: you organize also physical workshop training? Yes, also the training is included in the price in Prague, or we can make it online via, for example, this webinar. But yeah, the training is included. We can also organize training on your side, and there would be some additional costs or spend on traveling and accommodation, for example. But yeah, the training is included. Of course, it's a really important part to really push you in the beginning, because it's still CFD and sometimes quite complicated. But anyway, the software is very user friendly, easy to use, and smart. So I guess there are no problems using it. Okay, the next question, the same questioner is it possible to do in some way some optimization with this tool? The optimization tools in general are in the progress. They're in the development now. The optimization is for sure the biggest trend in turbomachinery simulations. So in general, yes, it's coming soon in one of the next versions. Nowadays it's manual optimization, right? So you load new model, test it. You load another model, you can test it. You can script the workflow. Of course, it's really automated. So, but in the manual way, yes, optimization is possible, but in the manual way. Maybe I will say just one point. Everything what you saw in this webinar can be automated, right? Maybe Radek, may I ask you, can you show the configuration file of the TurboMachine CFD, because that's a really important point, I think.
Yes, sure, I can.
Okay, thank you.
Okay,
because everything in TurboMachine CFD can be automated. We only think in automated sense, so everything what we do can be automated, used by another software or inside another software, or scripted to be really automated. So this is what you can see. You can see the configuration file, which can be written by another software or the optimizer, or really to make this you can just save this. You can just change anything, replace anything, and it still works. So it's very yeah, very automated and usable. Yeah. Okay. Thanks. Another question. Uh, yes. Yeah. Again from Pradeep now. Another quick question. Does this package also include other solvers like yes, CHD or combustion? Not directly. In the graphical interface, there is 100% of workflow is in the graphical interface, and in the graphical interface, you cannot choose other solvers, but TurboMachine CFD is fully compatible with standard OpenFOAM. So in the manual way, you can use for example TurboMachine CFD libraries like boundary conditions or yeah with other solvers. Yes, it's possible. Not directly, but from the command line, yes, you can. There is no combustion yet. By the way, the new big coming model is aeroacoustics, which will be released early next year in 2018. The aeroacoustics, and also real gases. Yes, so it's this. It's okay. Well, so I can't see any more questions. So I think it's time to conclude. So maybe we can switch the camera on to say hello. So yeah. Yeah. Hi. So it's us. So thank you for your attention. It was a pleasure being with you today. It's always a pleasure for us. So Radek, may I ask you to say something a little bit?
Let me just say thank you for watching us. Thank you. I hope it was interesting for you. I hope we tell you a lot of information about our software, and if not, so please do not hesitate to ask us, to contact us anytime with any problem, with any question. We are here to help you, and we are looking forward to help you with your problems and to help you in general. So I hope we stay in touch, and we are looking for your contact, let's say. So thank you, and have a nice day. Have a nice evening.
Okay.
Bye.
Okay, thank you, Radek. Yeah, this is really it. So thank you, everybody, for your time. Stay tuned, and we will be in touch. So thank you. Bye. Yeah. Bye. This is it. Finally. Yeah. Okay.